There was this cool Greek guy, and his name was, yeah, you bet it, you're destined for greatness if you're named Hero. He designed an engine. This was the first engine that had ever been designed. An engine, I guess I should define engine. An engine is something that, some that uses heat, that should be a usable contraction, some that uses heat to do work. So we're going to use heat to do work with Hero's engine. Hero's plan was this. Hero said, take a bottle and fill it with, I don't know, or you could take an Erlenmeyer flask or something, and you fill it with some fluid. Hopefully it's a brown fluid, because, you know, that's gross. And then you've got a top to this bottle, and it's doing something funky. It's kind of like, well, this is coming out towards you, and it's got an opening, and it goes back that way. And the other top to the bottle, there's like, that's the top, and the other top to the bottle is going back away from you. And so you can't see the opening. But that's the idea, and this is tightened on to the bottle. And what you're planning to do, this is away from you, and this is toward you. What you're planning to do is put a fire up under that sucker. Let's build a fire. I am really bad at drawing flames, but this is the idea, that it's hot down here, and you are adding heat, and you can get it to do mechanical work, because if steam comes out here, the steam will be expanding, and then expanding this way, and so that sucker will spin. And that's the simplest model of an engine that I can think of. It's pretty beautiful, and it will always spin the same direction every time you heat it. That's the simplest engine, and you can have enormously more complicated engines. Have you ever looked inside of a jet plane? I know I haven't, but boy, that would be a mess. But I need to make a schematic now for an engine. An engine needs two things. It needs a hot reservoir. And what I mean by reservoir what I mean by reservoir is a thing that's infinitely big and at a certain temperature, and it has a temperature T hot. Okay, cool, and you need, oh yeah, cool, right? You need a cold reservoir. That's this other thing that's also infinitely big. When I say infinitely big, I mean it is really big enough that it never changes temperature. And then you need an engine, and the engine acts in between those two things. Here it is. And the engine is taking in some heat from the hot reservoir. Let's see if we can draw those. Maybe we'll draw them in this color right here. The engine is taking in some heat, and we'll call this QH. That's the heat that comes from the hot reservoir. And the engine is doing work, like in this case right here. This engine can do mechanical work. You could mount a pulley on it and wrap something around and lift up a mass because it's spinning. Awesome. That's gravitational potential energy increase, so you're actually doing work. And that work we could put over here in orange. That's the work, and I'm going to draw that the work is a little bit less. See, the width of this is going to be corresponding to the amount of energy. That work is going to be a little bit less than the energy that's coming in by heat. Because there's a problem here. This is work out, that's the output work, and this is the input energy. That means we don't have 100% efficiency, but you know that energy must be conserved. And here's where the cold reservoir comes in. You must be wasting energy every time you use an engine. There is no way around this. The physics requires that there's some dumped out energy here, and the waste heat is called QC. And we could make ourselves an equation. Here's an equation. What I'm saying is the energy is conserved, and this equation will be the conservation of heat, energy, and work. So I'm going to say that the energy coming in must equal the energy going out. So I'm going to say QH equals work plus QC. You're not so interested in that. You're really much more interested in the work that you can get out of the machine, and that is the heat energy coming in minus the heat energy going out into the cold reservoir. And it's great that you need these things to be infinite. In principle, it's hard to get an infinitely big thing at a certain temperature and an infinitely big thing at another temperature. So you're often going to have to worry about changing efficiencies based on the changing temperature of these things. But let's define efficiency because we've been talking about it a little bit. Efficiency is a lowercase e for us, and that will be the work that we get out. Well, you know, if you work out, you win, right? The work that you get out divided by the energy that you had to put into the system. And what is that energy that we had to put in? QH. QH is the energy that we had to put into the system. And then we can say, oh, wait, this is just work out over win. That's just our definition of efficiency. Now, let's go on. The next thing that we can do is examine this efficiency a little bit more. Efficiency, we said, is work over QH, and I'm going to plug in our previous equation for QH, so it will be, oh snap. No, I'm going to plug in our equation for work. It's going to be QH minus QC over QH. And that's a lovely thing. The efficiency then is just 1 minus QC over QH. This is an equation they'll expect you to have memorized on the AP test. There will be like morning questions on this. The efficiency of an engine with a certain hot temperature and a certain cold temperature. Your initial instinct is to divide the cold by the hot or something. Don't do it. Don't do it. Use conservation of energy. This should be rather understandable for you. And then there was this guy. His name was Sadi Carnot. And he was French. You bet it. And he said, make, that looks like a colon too, make all processes reversible for maximum efficiency. And what we need to do that is to make sure that everything happens extremely gradually. And the way to make this happen gradually is to have these temperatures be very near to each other have these reservoirs be very near to each other in temperature, or to have an engine that just lets a trickle of energy come in and a trickle of work come out and a trickle of heat go out that direction. So this would be like everybody has their own energy generation plant or engine or whatever in their house, and they're all super tiny, and maybe you have millions of them. That's where we need to go as a culture. That's going to be really hard to do, though, because you have to build millions of engines. So that's a little bit annoying. Oh, there's more that Carnot said. Carnot also said, if all processes... This is great to be known for 2 sentences, right? Good job, Carnot. If all processes are reversible, then efficiency depends only on the temperature of the cold reservoir and the temperature of the hot reservoir. And that led Lord Kelvin. Lord Kelvin was a serious thinker, and we've seen his name already. But Lord Kelvin said, hang on, Carnot. Kelvin said, if the efficiency depends only on the temperatures, and furthermore, the efficiency is this other, what was it, efficiency is 1 minus QC over QH. Could we also say that's equal to 1 minus TC over TH? And it seemed that it was. And so Lord Kelvin developed a new equation, in fact, a new definition of temperature, and that is Tc over Th equals Qc over Qh. And you can define temperature based on the heat that's flowing in an engine. And this statement that all processes being reversible and efficiency depends only on the temperature, this is actually a restatement of the second law of thermodynamics. And you also might agree that if I had this engine here, this engine could be less than maximally efficient. This is the most efficient it can possibly be. So every step needs to be reversible. But in principle, that is incredibly slow to do things reversibly. You've got to speed things up if you want to, say, drive a car. So you make efficiency sacrifices. And then we can say that instead of saying this is the definition of efficiency, work over QH, and this other thing right here, we're going to say this is maximum efficiency. And you'll be lucky if you can get it. But if somebody says to you, this is an excellent way to evaluate claims of people who want your investment money. If someone says, hey, I made a 90% efficient engine, you'd be like, what? Because you'd need to have an enormously big hot temperature and a cold temperature very near absolute zero. And how are you going to get that sort of thing? How are you going to get that sort of thing? Because if you know the two temperatures, you can always find the maximum efficiency. So be careful and do not run into any scams. If we know maximum efficiency, then we also know the maximum work that we can get out of an engine. So the work maximum that we can do is the maximum efficiency times the temperature of the hot reservoir. Let's see if that makes any sense. I'm just solving this equation for work, multiplying by QH on both sides. So I'm taking maximum efficiency and multiplying it by QH, so that then the maximum work we can get out is 1 minus the temperature of the hot. I'm using Lord Kelvin's definition again here. Temperature of the cold divided by the temperature of the hot. That efficiency multiplied by QH. There you are. That is the maximum work that you can get out of an engine based on the constraints of the hot reservoir's temperature and the cold reservoir's temperature. Goodbye. Some that uses heat, that should be a usable contraction. Some that uses heat to do work. So we're going to use heat to do work with, like, that's the top, and the other top of the bottle is going back away from you. And so you can't see the opening. But that's the idea, and this is tightened onto the bottle. And what you're planning to do, this is away from you and this is toward you. What you're planning to, there was this cool Greek guy, and his name was, yeah, you bet it, you're destined for greatness if you're named Hero. He designed an engine. This was the first engine that had ever been designed. An engine, I guess I should define engine. An engine is something with Hero's engine. Hero's plan was this. Hero said, take a bottle and fill it with, I don't know, or you could take an Erlenmeyer flask or something, and you fill it with some fluid. Hopefully it's a brown fluid, because, you know, that's gross. And then you've got a top to this bottle, and it's doing something funky. It's kind of like, well, this is coming out towards you, and it's got an opening, and it goes back that way. And the other top to the bottle, there's